Hello everyone, this is Zain with another episode of the revision challenge for computer science AS. So today we'll talk about video and compression techniques. Video is in widespread use on computers for recreation and educational use. YouTube is one of the most popular websites where users can post their own video content. Videos are also a medium for an explanation of the working of a piece of equipment or to provide a learning tutorial like this one. A video is a sequence of still photographic images which are displayed in sequence. The frequency with which they are displayed gives the appearance of continuous motion, and what is contained on individual frame is not apparent. The frequency with which the frames are displayed is called the frame rate. A sequence of frames in a continuous effect to the human eye is achieved with a frame rate of 25 frames per second or maybe higher. So now we'll move on to different types of encoding that is used for videos. Basically, encoding is how a video is stored and how it is recorded. So there are two types of encoding that we'll go about. The first one is progressive encoding and the other is interlaced encoding. A system which stores the data for an entire frame and displays all the data at the same time is called progressive encoding. This means the frame rate will be the number of pictures displayed per second. Traditional film uses progressive encoding. The other is interlaced encoding. The problem is that some devices such as television are not designed to display all the frame data at the same time. The data from a single frame is encoded as two separate fields, one containing the data for the even numbered rows and the second frame has the data for the odd number rows. The term interlaced comes from the concept that the image is rendered by switching between the even and the odd fields. It follows that the rate of the picture display is twice the frame rate. With increasing demand for the display of video content through DVD players, set-top boxes, and other home electronic devices, there is still a need for interlaced encoded video format files. The picture frames that make up interlaced fields have a correct order related to each other. So these orders are, the first one is the special order, which should be the even or odd field. The temporal order refers to a field or frame and which field represents an earlier moment in time. If either one or both of these orders is incorrect, the result of the playback will appear as jerky motion or blur edges to the content. So now we'll move on to the new topic, that is compression techniques. Both sound and video files tend to have a large file size. Techniques used which encode the data in a way which results in less bytes for the file are highly desirable. Compression is the technique of reducing the size of a file without a significant loss in the later quality in the use of the file. So there are different techniques for file compression. The first we'll go about is the image compression technique, which is run length encoding or RLE. Consider a bitmap file of a photograph where over half of the pixels are the same pixel value, representing the blue sky. An alternative to saving, say, the consecutive 300 pixel values on a row could be to save a single copy of the pixel values followed by the number of occurrence of the value 300. This way, we have reduced the number of pixels used to store this portion of the graphics from 300 to a very small number. This technique would be appropriate for a monochrome image consisting of a black line drawing on a white. So consider this image. This image is 30 by 4, so 30 columns and 4 rows, and each pixel value holds a single color. The first row pixels could be encoded as, so we first need to count the number of same pixel in consecutive occurrences. So this is W1, 2, 3, 4, 5, 6, 7, 8, 9. So this becomes 9W. Then we have 1, 2, 3B, then 1W. So 3B and 1W. Then we have 1, 2, 3, 4, 4Bs, and then 1, 2, 3, 4, 4Gs. So 4B and then 4G, and then we count the rest of the values for W. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. So again 9W. Assuming each run number is stored as a single byte, the first line will be stored using 14 bytes since we have 14 different columns. This is an effective compression. So we'll do the same process for the other rows as well and store them separately in other lines. So that's how you compress an image using RLE. There are two types of encoding that we'll go about. The first one is lossless encoding, the other is lossy encoding. In lossless encoding, we have two alternatives for encoding a bitmap image: either to save the color code for every single pixel or to use RLE that we already discussed. Both of these techniques means that the original bitmap can be recreated when the data is read from the bitmap image file and displayed on the output device. For bitmap files, several of the universal file formats are lossless. These include .bmp and the portable network graphics .png, which was intended as a replacement for the older .gif format. The other is lossy encoding. Using a lossy technique for encoding bitmap data has the objective of compressing the file size. Lossy techniques are based on two concepts which exploit the limitations of the human eye. The first one is that an image which has a large background could encode the background pixels with a lower resolution. Colors such as blue, to which the human eye is less sensitive, could be encoded at a low resolution. So that's the second concept. The popular .jpeg file format is lossy encoding format. So then we move on to video compression techniques. Since a video is made up of a number of frames, we are interested in applying various compression techniques to a video frame or a frame sequence. So there are two types of redundancies that we solve in video compression. The first one is special redundancy. This is similar to the concern about redundancy in a bitmap file. So is there any sequence of the same pixels within a single frame which could be encoded or effectively compressed? And then we have temporal redundancy, in which we see that there are a sequence of similar pixels in the same position in consecutive frames, in which case we do not need to repeat them in each frame. It will depend entirely on the content. A room full of people discussing or dancing will not compress well as a panoramic view of a beauty spot. Inter-frame encoding addresses the issue of temporal redundancy. The encoding method is based on the idea of keyframes, which store data for all the picture, and intermediary frames, which store only the differences from the next intermediary frame or keyframe. Over the years, standards in the computing industry have emerged for file images. We have already mentioned .bmp, .png, .gif, .jpeg, and sound data. Popular sound formats include .wav, .mpeg, and .mp3. Video, which is a combination of moving pictures and sound, requires its own industry standards. The detail about encoding methods used for this is outside the scope of our syllabus. The key issue is that there is correct synchronization between the picture display and accompanying sound commentary. The current popular multimedia container formats or MCFs include AVI, MOV, MP4, and Matroska. The differences between container formats arise from issues such as popularity, overheads, and support for advanced codec functionality. So this is the end of our day 3 for the revision challenge. This ends our first chapter for AS. From tomorrow, day 4, we'll start with communication and internet technologies. So see you guys tomorrow. If you like this video, please like and share with your colleagues so they can also use this as revision content. And please subscribe to my channel so you can get more content on videos, and plus I will be posting past paper solutions and pre-release material on this channel only.